Hi friends, welcome back to yet another video. In this video, what I have got for you is a couple of easy questions, which was which were asked in GATE 2019. So I have two problems. Let me get started with the less interesting one. So the more exciting one I'm keeping for the later part of the video. So the problem goes like this. You're doing a high cycle fatigue test. A metallic specimen is subjected to cyclic loading with a mean stress of 140 MPa and a minimum stress of minus 70 MPa. The R ratio, which is the ratio of minimum stress to maximum stress for this cyclic loading is. I think this is a fairly easy question because usually they never used to give us what is the definition of R ratio, because I remember back in 2015 I guess, or they asked a similar question and they were not giving you the definition for R ratio. The moment they give you the definition and for R ratio, the question is fairly boils down to simply plug and check. They are telling you it's a high cycle fatigue test, so you can simply plot all these things and a curve like this. So as you can see over here, the stress is varying in a cyclic fashion or a sinusoidally, whatever way you would like to call it. Then we have a mean stress of something like 140 MPa and the minimum stress is minus 17 MPa. So from this we can compute the amplitude stress, which will be 210, isn't it? You don't need calculus, you don't need logarithmic tables to tell what is the amplitude stress. It's simply 210. Clear? Because that's the difference from the mean to the, you can tell that's the high difference between the mean point and the trough. Now you know the trough point is this, which is corresponding to minus 70 MPa. You know your mean position is 140, then you can simply tell your peak will be 140 plus 210, because that's why you, so this is your amplitude. So this is your one amplitude, these two. So you know A now. A is same in both directions, even though the figure doesn't look like that. Apologies for that. So now your maximum stress is 140 plus your A. So that will be something like 350 MPa. Now you know your maximum stress, you know your minimum stress. You're asked to compute this R factor, which or whose definition was given in the problem, but usually they don't give it. So better you memorize or you understand what is this quantity is, or this quantity of R. Sigma is minus 2. A couple of things I would like to tell you, because since I see for a completely reverse loading, what would be the value of stress ratio R? The value of stress ratio will be minus 1, because your sigma max will be equal and opposite to your sigma min. So that's why you will end up with an R ratio which is equal to minus 1, this for a completely reversed loading. And this is how you plot your SN diagrams and all. Stress life plots and all these things are plotted, or they are found out after performing tests with R equal to minus 1, or after performing completely reversed loading cycles, to ensure that the mean stress effects don't creep into the picture. The moment mean stress effects creeps into the picture, then you need to use your Goodman law or Gerber law, your Soderberg equation, and all those things should be used once you have mean stress in your problem. So that's a bit of information for you who watch my videos. So this may be another question, or you will get some information to answer similar questions that will come in the future exams. Good. So now let's go to the very important problem, very interesting problem, I would say, because I like this kind of problems. So you get to work, you won't remember all your long formulae for your principal stress. You won't use your formulae for what you call the Mohr circle. You won't remember your equation for a lot of stuff, but you have to remember this kind of simple things. So this is yet another interesting problem. I request you to go through the problem once. Uh, so, because the answer is itself there in the question. So, consider the stress strain curve for an ideal elastic plastic strain hardening metal. As shown in the figure, the metal was loaded in uniaxial tension from the starting from O. So, you all of you would have done some uniaxial tension test in your college. So this is how you load the specimen you get here, and then it strain hardens to point Q where the loading was stopped. So you unload your specimen at this point and then drops back here. I would like to explain you a couple of more things here. I guess that's good. I guess because see, the strain can be decomposed into two components at this point. This is your elastic strain, which is recovered. This is your elastic strain. Okay, this is your elastic strain. But this is your epsilon plastic, which is not getting recovered. So your total strain is epsilon plastic plus epsilon elastic. I wanted to tell you this one piece of information. How is epsilon elastic related to your stress and Young's modulus? At any point in your loading regime, always your elastic strain is related by your stress divided by Young's modulus. Okay, so this is an expression for your elastic strain at any point in your loading curve. Okay, so this is one good useful formula which you can remember for a long time, I guess, whenever you learn a lot about plasticity and all. But now the question in this problem is, if the same specimen is reloaded in tension from point R, now we are trying to reload the value of the stress at which the material yields again. Now coming to the explanation side of things, so this material is undergoing strain hardening. It is having that characteristic of strain hardening. It is behaving, or it is exhibiting that characteristic of strain hardening. So what happens is, as you load the specimen from point R, it will behave linearly up to this point Q, or in other words, its yield strength has increased from 180 MPa to 210 MPa. The material is more strengthened. Why is it so? It is so because when you yield, when you subject, or when you take a material and when you subject the material to yielding, dislocations will be created. Dislocations will be created. As you know, dislocations are the reason why our actual yield strengths are very less compared to the theoretical yield strengths. So when you subject a particular specimen to yielding, there are more and more dislocations will get developed inside the material, but it doesn't weaken the material. Intuitively one can say, I'm subjecting the material to yielding, so I'm creating more and more dislocations in my material, but I'm not weakening the material. What happens is, the yield strength of a material is related to the easiness with which the dislocations can move inside a material, or the easiness with which the dislocations can slip along a particular plane in a material. So when you strain the material beyond this yield strength point, what happens is more and more dislocations get created, and because of this process or the phenomenon called the dislocation interaction, the mobility of the dislocations get reduced, or the motion or the movement of the dislocations get obstructed, and it further increases the yield strength of the material, because yielding is simply the movement of dislocations. Now the dislocations are not allowed to move that easily, which means your yield strength increases from 180 to something like 210, and the material behaves as linear up to this point. Believe me, once you start working, you will run into a lot of applications where this particular concept will be handy. So this is something which you should remember for ages to come, and which should you should know this thing like the palm of your hands or whatever you say. Thanks for watching. So the key concepts, one was the stress ratio in a cycle fatigue test, and then this concept of strain hardening. Thanks for watching. And one more reminder, not all materials show or demonstrate this strain hardening behavior. There are some materials which demonstrate softening also, and all these things will be learned and discussed in detail when you take a plasticity course. And one another point to take away is this particular thing: at any point in your curve, the elastic strain can be related to the total stress divide as related, or can be defined as the total stress divided by the Young's modulus. Thanks for watching.